one way to predict the pH of a solution and therefore the ending of the titration, the reaching of the equivalence point, is to use pH meters, which actually tell you the pH of a solution as it's changing. But a somewhat simpler way, or at least a lot cheaper, is to use acid-base indicators, which change color depending upon the acidity or basicity of the solution nearby. So as an example, we might take some protonated form of the indicator. Now this can, being an acid, dissociate into a proton and the conjugate base. So we can often see that the protonated form, the acidic form, has one color, and the deprotonated form, the basic form, has a different color. And by the presence of these colors, we can tell which of these we primarily have. This implies the acidity or basicity of the solution. This acidic form will have more often than the basic form if we have an acidic solution. Because having a high concentration of protons in an acidic solution should shift this reaction to the left, should give us a lot of the protonated form. Whereas this basic form, the deprotonated form, will find very much in basic solution. Because in a basic solution where you have a lot of hydroxide, that consumes the protons, driving the reaction to the right and giving you a lot of this deprotonated basic form. And so I guess two examples of these are phenolphthalein. In an acidic solution, you have a colorless form, and in a basic solution, it's pink. You've titrated with this multiple times over the last year or two. We also have methyl red. In acidic form, it's red, and in basic form, it's yellow. Now, these acids, these indicators, which are acids and bases, they have certain pKa's. Phenolphtalene's pKa is 1.0 times 10 to the negative 9. Having this certain pKa, we can predict the pH range over which it will change significantly. And so consider that the pKa is 1.0 times 10 to the negative 9. Take a look at that 9. Having a pH of less than 1 and greater than 1, that is where you'll see the significant change in color. So less than 1 from 9, which is 8, and then greater than 1 from 9, which is 10. This is because we can see significant changes in the pH when we have variation between a 10 to 1 and a 1 to 10 ratio between the acid and base forms. So if you have, for example, 1 over 100 or 1 over 1,000, you will, in phenolphthalene's case, you'll see much less of this acidic form than you will in the 1 over 10 ratio. So we generally say that between the 10 to 1 and the 1 to the 10 ratio, in concentrations between our conjugate bases and acids, we see significant color change. Now, if our pKa is 9, then we'll have a 50-50 mixture of the acid and base form at a pH of 9. We know that we have a 50-50 mixture of these two things when the pH is equal to the pKa, because when the base and the acid form are equal to each other, we have a ratio of 1 to 1. And taking the log of this 1, that ultimately is just equal to 0. And so, yes, at a pH of 9, we have a 1 to 1 ratio, and at a pH of less than 1, we have slightly more of the acid, 10 acids to 1 base. And at a pH greater than 1 of this middle point, we have a slightly more basic solution, so we have slightly more base than acid, 10 bases to 1 acid. And so this allows us to predict the pH ranges of change. So what kind of indicators would you use for a variety of titrations? Consider a case in which you are titrating a strong acid with a strong base. So start out with a strong acid, you have an acidic solution, and add strong base to it. The pH increases as time goes on, and then it gradually increases in rate of change until you reach that inflection point, your equivalence point, where all of that initial strong acid has reacted, presumably, and you're only now adding additional base. So your objective in this titration is to determine at what volume have you reached the equivalence point. This is your objective. So it's important that you find this volume to be about equal to where this equivalence point, maybe slightly further, but not significantly ahead. Now, which indicator should you use? Methyl red, which changes pH between color between pHs of 4 and 6, or phenolphthalein, which changes color between pHs of 8 and 10. Well, if you were to use a methyl red, it would start changing pH at about changing color at this pH of 4, which would give you a volume which is significantly before the equivalence point. And so you don't want to use methyl red in this case. But if you were to use phenolphthalein, then it would change pH almost exactly at the volume that your equivalence point is at. And so this is a proper choice for your indicator. Generally, you want to use an indicator which changes color slightly after the equivalence point is reached, or while the equivalence point is reached, but definitely not before. Choose phenolphthalein because the equivalence point is reached slightly before the color change occurs, or during the color change. Do not choose an indicator which changes color significantly before you've reached the equivalence point. You can see a significant difference in the volume of sodium hydroxide added. Okay, take another case in which you were to titrate a weak acid with a strong base. This time, you start with a less acidic solution, and your pH increases until you reach the equivalence point, which is notably above a pH of 7, whereas the pH was 7 at a strong acid, strong base titration. Now, you again want to use an indicator which changes color right after the equivalence point or during the equivalence point. So in this case, the equivalence point that is reached while the phenolphthalein is changing color. And so if you choose the phenolphthalein, you choose the point where you start getting color change, and that is almost exactly at where the equivalence point is. And so phenolphthalein is a fine choice. But what about in this case, where we do a strong acid weak base titration? So start with a weak base, add acid to it. Here your equivalence point is significantly below 7, perhaps about 5. You want to choose an indicator which changes color, I guess, during the change in equivalence point or slightly after. And so here, methyl red is a good choice. It changes color at this pH, which is almost exactly the volume of your equivalence point. Whereas if you were to choose phenolphthalein, you would get a color change quite a bit before you've reached the equivalence point. So I think the key summarizing facts is you want to choose an indicator which changes color while the equivalence point is being reached or slightly before. Thanks for watching, guys.